So hello, everyone. Thank you so much for joining us today. We are the Pittsburgh Java User Group. I'm Sirisha, and I've got Renat here as well. You can follow us on our on the Twitter platform. That's the handle right here. And you can register for our upcoming events and learn more about Pittsburgh Java User Group on the meetup page itself. That's where you were all there. So you already know about the meetup. We have all of our 2021 and 2022 recordings up on our YouTube channel. So please subscribe to it and you'll get notified of our recordings as soon as they're uploaded. We would like to thank our official sponsor, which is JFrog. And with that, Gerrit, I'll hand it off to you. If you could just quickly introduce yourself and then carry on with the presentation.
Sure. Let me share my screen.
Yeah.
Here we go. All right. So you can see the screen?
Yep.
Okay, perfect. Let me just close the chat here. Okay. So yeah, welcome to the session, What the CRaC, Coordinated Restore at Checkpoint on the Java Virtual Machine. My name is Gerrit Grunwald. I'm working for Azul Systems as a Senior Developer Advocate and yeah, doing all things Java. So I did a lot of front end and now more back end and JVM stuff. So yeah, whatever it is, Java is the best. And that leads me directly to the topic. First of all, the slides, you can also get them here if you like, but I can also provide them because I change them all the time. So this link is a little bit older, but if you like, you can get the old ones on SlideShare. So Java is great. I think we can all agree on that one. We have a vibrant community, as we can see here, right? I mean, I don't see you, but at least I see that there are people in the session. And we have hundreds of Java user groups, and we have thousands of free open source software projects. But the real star of the whole Java ecosystem is the Java virtual machine. I think this is a fact, right? It doesn't matter which language you like. If it runs on the JVM, then it's great. So the question is, how does it work? I mean, most of you will probably know better than me, but nevertheless, I will give you a very simple introduction on the parts that are interesting for this session. So let's start with a Java file where we have our source code, and then we put that in a Java-C compiler, and it spits out a class file, which contains cross-platform bytecode. Means if you have this class file, you can load it on every JVM that is available on any platform that you like. And then we take this class file, put it in a so-called class loader, which is here very simplified. The class loader alone is quite complex, and loads it into the JVM memory. And once it's in the JVM memory, it gets into the so-called execution engine. And you already see that the execution engine contains multiple parts where we have, for example, the interpreter, and we have the C1 JIT compiler, that is a formerly known client compiler. And we have the C2 JIT compiler as the formerly known server compiler. And then there is a profiler and garbage collector. In this session, we only need to know about the first three things. And to give you an idea of what's happening there, so I try to explain it very simply. So first of all, the interpreter takes the bytecode from the class file line by line and interprets it into the instruction set of the CPU. And the JVM is watching that, and it's counting method calls. And once there's a specific threshold in method calls, when it's reached, it takes this code and then passes it forward to the C1 JIT compiler. And the C1 JIT compiler is a very fast compiler and does not do a lot of optimization. So it's really just, most topic is compile as fast as possible down to native code. The reason for that is, I mentioned that already, it's the formerly known client compiler. And if you, for example, start IntelliJ IDEA or Eclipse or NetBeans, which are all Java programs, you would like to have them, once you double click the icon, it should just pop up and start. You don't want to wait for the compiler to do the best optimizations ever and wait for 10 seconds just to start up the IDE. So that's the reason why the focus for the C1 JIT compiler is compile fast, don't do a lot of optimizations. So, and then this code in the C1 compiled code is running, and the JVM again is watching that and profiling it and counts another time how often this code was called. And then when another threshold is reached, it takes this code and forwards it to the C2 JIT compiler. And the C2 JIT compiler is more complex than the C1 compiler. It's a formally known server compiler. That means it takes longer to compile, but it creates much better code, so higher optimized code. And these higher optimizations take longer because where we came from, it was application servers, and usually you start them once, I don't know, a month or every couple of weeks. And so the startup time was not really a big problem here. So this is how it works in principle. And if we take a look from a different perspective, then this is the so-called execution cycle. Then we have the interpretation first, which is slow. Then we have a profiling phase, finding the hotspots, pass the code to the C1 compiler, again profile this code, and then forward it to the C2 compiler. And then there's this other thing that you see here, which is called de-optimization. So you might ask yourself, why do we optimize the code if we then de-optimize it, right? So, and there's a reason for that. Let us take a short look at the optimization. So if we have some code like this on the left side here, which is just a method that computes the magnitude of a given value, and then we see it checks the value. If it's greater than 9, it computes the value, and if not, then the bias is just 1, and then it returns the mathlog 10 from bias plus 99. This is the method. And so if now, for example, the value was never greater than 9, right? So that means in principle, the result is always 1. Then we can do something like this. And this is what the compiler will do. It will, the whole block that we had before, this one, where the BIOS was computed and all that, it will go away, and we have something like an uncommon trap method. And this will only be called if the value is greater than 9. That means per default, it will always return 2. Because 1 plus 99 is 100, and mathlog 10 from 100 is 2. So, and you can imagine that this code is much faster than calculating all the time the log 10. So if now we get a value that is greater than 9, then this left method is not valid anymore. So it means the compiler can't use it. So, and for that reason, it will de-optimize. It will take the compiled code, the optimized code, throw it away, and go back to the whole method that we saw before, and does another interpretation, C1, C2 compilation. So it goes through the whole cycle again. This is in principle the optimization, and this can be a performance hit, as you can imagine, right? So you optimize the code first because the compiler did some branch analysis and figured out, oh, this part of the code I can optimize for this specific way of computing. And when this way change and is not valid anymore, it has to throw away the compiled and optimized code and do again the interpretation C1 and C2 compile. So, and this is a performance hit. On the other hand, this is also a benefit because the code it's more dynamic, right? So if you have your application running and something changes in the behavior, the JVM can adjust to that by de-optimizing and do a new run and optimize again. So if we take a look at the JVM performance graph, we see these 3 different colors, the yellow one in the lower left, and then green, and then blue. The yellow one is the interpretation phase, and you see it's just a short phase, and then it gets into C1 compile and profiling phase, and then finally into the C2 compiling and profiling optimization phase. And you see that the performance then really goes up until it reaches a specific level. And then we see on the right side this periodic like trenches here, and this is the garbage collection process. That means if the garbage collector does stop the world, then of course we have performance hit. And these bigger trenches here in the beginning, this is the optimization. So it means during the the speed up phase of the JVM, there are situations where the code was already optimized, has to be de-optimized. We see huge gaps here, and then optimization starts again, and so on. Finally, at one point, we only have the garbage collector process in the ideal case. So that's all great, but you can imagine it takes time because nothing is for free. And that leads me to JVM startup. And this is the point where people talk about, well, you know, the JVM startup is so slow and all that kind of stuff. You know that. If you work in microservice world, then you probably heard that. But if we take a closer look at that, then the JVM start itself. So if you just take a JVM and you create your Java class, just one class, one method, and you just say, system out print line hello world. Compile that and tell me it's slow. It will be fast because it's nothing to do. It's just the JVM itself plus the one class. There's not a lot to optimize, right? So that means the JVM itself starts up quite fast. It loads some stuff, it initializes and does some optimizations, and then your application comes into play, and that makes it slower, right? It all depends on your application that has to be loaded by the JVM. Then it has to initialize all the resources, some application-specific logic, and also optimizations. So, and these two things together usually is defined as the JVM startup, or the time to first response of your application. That means only because your application responded for the first time doesn't mean it's fully optimized, right? There is more. So because your application itself can also be warmed up, right? So that the JVM will do more compiles and decompiles and optimizations, and the application you will maybe apply some specific workloads to warm up your application. And this whole thing is then referred to as the JVM warmup. So, and people sometimes mix that up, right? So it's just to let you know, if we talk about JVM startup, we talk about the time to first response. It's the first two parts on the left side. Okay, so if we take this to the microservice environment that we have today, then that means first time we run a microservice, we have to warm it up or start it up. So it takes time. Second time again, third time again. That sucks, right? It's just, why should we do that all the time? Wouldn't it be better if we could do something like we warm it up first or start it up once, and then the second time we just go full performance with no overhead, and from there on every start will be full performance. That would be great. So let's have a look at some possible solutions here. First of all, there's class data sharing. And what it is, it's called CDS. There's app CDS and dynamic CDS. And usually it's a representation of the classes, the internal representation in one file. And you can imagine when the class loader starts loading all the classes from all the dependencies all over the place, it takes some time to look them up, to load them, and then load them into the memory. So if you then instead load this stuff once, dump all this stuff in one file, the next time you start up, you just load this one file. And because it's already an internal representation, it's much faster, right? So this is CDS, and it's per default enabled since JDK 12. So that means if you're on JDK 17, you will already use that. And it came the first time with JDK 5, if I'm right. So that means you can share these class representations on each JVM start. And there's no optimization or hotspot detection here, right? This is just class loading. That means it reduces the class loading time of the JVM. And you can gain up to 2 seconds startup time just by tuning the CDS correctly. And there is a nice blog post from Ionit Balozin, and you can find it in that link in the lower right corner. And he does sessions only about CDS and tuning it. So it's quite interesting. If you never heard about it, it's worth taking a look. Okay, so that means it happens there. So add the class loader, not interpretation, no compile. So it has nothing to do with this ramp, this curve that we saw. It's just before that. But still, we can improve startup time by up to 2 seconds just by tuning this. Okay, that's cool. But it doesn't really help us with the interpretation, compilation, and all that stuff. So then there is ahead of time compilation. You probably all heard of that. That means if we do AOT, then we don't have to interpret bytecode. We don't have to do any analysis of hotspots. There's no runtime compilation of code, and we can start up at full speed straight away. And Graal native image does exactly that. So that means problem solved, right? Well, not so fast. So AOT is by definition static. So that means the code is compiled before it is run. And the compiler has no knowledge of how the code will actually run. So it just takes the code, compiles it. So that means it's not like the JVM that can do all the optimizations and stuff up front or at runtime. So the AOT will just take it and compile. And there is one thing that helps. It's the so-called profile guided optimization. And what it does is, if you take RAVM, for example, it comes not only with the AOT compiler, it also comes with the Java compiler, with the JIT compiler. So what they do, you run the application once using the JIT, and you profile it. You save the profile of that application, And then when you create the native image, you apply that profile to the native image. And so you gain some performance, but only once. So it's just from this one profile, and that's it. And this is only available in the Enterprise Edition. So if you use GraalVM Community Edition, the free one, then you can't use PGO there. So if you take that to the JVM performance graph, and this is not really hard numbers now because it really depends on the application that you compile, but usually you get up to 60, 65% by plain AOT approach. If you then use PGO, you can gain up to 90. Sometimes you can reach 100%, and that always depends on your application. So there's no general rule here. And you need to run the profiling with the JIT first to do that. Okay, so if we do a quick comparison between AOT and JIT, then that means AOT can't use, or it can just use a limited method inlining, because this is only possible during the profiling phase, where the JIT can do that all the time. So, right, so also there's no runtime bytecode generation in AOT where the JIT can do that. Reflection is possible in AOT, but it's quite complicated. It's not so easy, where in the JIT it's pretty simple to do reflection. And you can't really use speculative optimizations. This is the stuff that I showed you with the branch analysis. So the JIT can figure out at runtime what is the most used part of the code and can optimize the code for this use case. And the AOT, it can do something similar at the profiling phase, but it can't change it anymore. So once it's compiled, it's done. Where the JIT is something like the ongoing profile guided optimization. It does that all the time. That means the overall performance of the AOT approach is typically lower than the JIT. But the biggest problem that I see with the AOT approach is that we are Java developers. We code our stuff in Java or something on the JVM, then we compile it, and then we profile it and all that. We run our tests. This is all Java. So if something went wrong, so we can just debug it with the Java IDE or with some Java debuggers. If you use AOT, we jump out of the Java world into the native world and create a native image. And this is hard to debug because this is not Java code anymore. This is native code, and this is different from JIT code. There are ways to do it, and the GraalVM team does improvements to support debugging for native images, because it's really hard. It can happen that you run all your tests and everything's green, and you create the native image and it will fail in production. So I had people that came to me exactly with that problem and told me, what should I do? Because I can't really debug it. But this is getting better. On the other hand, the native image, of course, starts at full speed, right? It doesn't require a warm-up or startup time like the JVM does. And we don't have any overhead to compile code at runtime. So because we did all that when we created the native image, we have all this overhead is done there, where the JIT does it at the startup. So it means it starts your application, interprets it, compiles it, and at the same time, the application is already running. So it means we need more power here. And also the memory footprint is different because the AOT approach only compiles all classes that are used, where the JIT always loads every class that you have on the class bar, right? So if you load a library and you just use one class, it will anyway load also the other classes. So we need more memory for the JVM. And this is a little chart that I found that gives you the whole thing that I told you just in one chart. So that means the startup time is better with AOT. The throughput is better with the JIT. Memory is better AOT. Reduced max latency means this is related to the garbage collection. I think GraalVM only can use serial GC. Maybe they can also use G1 in the meantime. The packaging is more or less the same with both of them. So let's take a look at a different approach. And for this, we need to introduce a project which is called CREO, Checkpoint Restore in User Space. And this is a Linux project, which is part of the kernel since 2013. So it's quite old, right? And it was made to freeze a running container application and then save this state of this application as a checkpoint to the disk and restore this state later on back to memory. So the idea is, in principle, if you have a laptop and you work with that and you finish in the evening, you just shut the lid. And usually the next morning you just open it again and you will continue working at the same situation that you left it the day before. This is exactly checkpoint restore. So the operating system will detect that the lid was closed. It will store the state on the disk. Once you open it again, it will load the state back into memory. So, and CRaC was made to do this for Linux applications. And keep that in mind, it's only for Linux, no Windows, no Mac. It's already used or integrated in OpenVZ, Linux containers, Docker, or Podman. That doesn't mean it's always used, but you can use it there. So that means you can use CRaC, which is also a command line parameter, to checkpoint a Docker container. That's possible. It heavily relies on the proc file system. And that means this is, for example, the reason why it's not available on Mac. Even Mac is a Unix-based system. It doesn't have proc, so there is no way to have CRaC there. And there are also Linux distributions that don't use the proc file system. And then you probably can't also not use, you cannot use proc or CRaC. So, and it can checkpoint lots of stuff. So it can checkpoint processes and threads, application memory, memory map files, shared memory, open files, pipes, FIFOs, sockets, inter-process communication channels, and timers and signals. And it can reopen or rebuild a TCP connection just from one side. So you don't need this handshaking that you usually need. So that's quite interesting. But of course, with everything, it doesn't come without challenges. So one of the challenges is if you create a checkpoint from an application on one machine and you take the checkpoint and copy it on another machine, you can't just simply restart it there. First of all, the machines have to have the same architecture. It means you can't use something from an x64 machine and restore it on an ARM machine. That doesn't work. Also, if you have open files on the one machine, you need to have the same files on the other machine. Of course, this won't work, right? And shared memory the same. So the other thing is you can't really start multiple times the same or restore multiple times the same state. It's not possible because the PIT, the process ID, which is unique on Linux, is part of that this snapshot or the checkpoint. So that means once it's restored, you can't just restore it again because the PIT is already taken. And you guess right, if the PIT is already taken by any other process, it won't work. We are working on a solution to get around this problem with the PIT, but still, it's a drawback. But the biggest problem is if you think about the JVM, it's an application that runs on Linux, so I should be able to checkpoint it with CRaC, right? And this is correct. The plain JVM, you can checkpoint with CRaC, and that's not the big problem. The biggest problem is your application is running in the JVM, and your application has database connections open, it has files open, or whatever sockets to whatever web services. And now if you just checkpoint the application and shut it down, then, no, not the application, the JVM, then your application has no idea what's happening, right? So it means you checkpoint the JVM, it will be shut down. The next time you restore it, it will maybe restore the JVM. And then once your application will start, it will figure out, oh, wait a minute, where's my database? Where's the open file? It's not there because it was also closed when the checkpoint was created. So that's the problem here. And that leads me to CRaC. And it means coordinated restore at checkpoint. And the biggest part here is coordinated. So what we try to solve this problem that the application needs to know when there was a checkpoint and when there was a restore. So we have a running application and we would like to let the application know, now there's a checkpoint, you can do something. And then when it is restored, we let the application know, now you got restored. And the reason for letting the application know, I will come to that in a second. So CRaC comes bundled with CRaC. It's a specific version of CRaC that we provided to the CRaC source code to make it possible to talk to the JVM. And we clean and compact the heap. So in principle, it's the same as a garbage collection mechanism, right? So the JVM is in a safe state when we create a checkpoint. And it comes with a pretty simple API. And it creates checkpoint either using code or using JCommand. So that means you can either use it from within your application or you can do it from the outside. And it throws checkpoint exceptions in case you forgot something. It will tell you there was a problem when we created the checkpoint, there was still a resource open, for example. So we added to make all that possible, we added two command line parameters to the JVM, which is -XX CRaC checkpoint 2. And then you give as a parameter, you give a folder name. Right? And the idea is that once you start your application, you pass this folder to the JVM. And when there is a checkpoint, the JVM stores the checkpoint to this given folder. So you can decide at startup where the JVM should store the checkpoint data. And when you restore from that checkpoint, you just call java -XX CRaC restore from and point it to the same folder. And then if there is a checkpoint, it will restore from there. So that's the two commands that we added to the command line. The whole thing is an OpenJDK project. So that means even if we created it at Azul and it's led by one of our engineers, Anton Kozlov, we provided that code to the OpenJDK project. And you can find it on openjdk.org/project/CRaC. And there's also an OpenJDK version that you can download and install. And this is Oracle OpenJDK. So it's not something from Azul like Zulu or something else. So it's just a plain OpenJDK version where we added CRaC to that OpenJDK. So the CRaC API is pretty simple because it only contains one interface, which is called resource. And it has only two methods, before checkpoint and after restore. And the main idea is that you as a developer have to add this interface implemented in all classes that somehow have resources that are interesting. And this is mainly open files and sockets. So if you have something that has, for example, a database connection or connects to any other service, this is probably the class where you have to implement this interface. And then somehow you have to let the JVM know that you implemented this interface, because the JVM, in case there's a checkpoint, needs to know, okay, what are the classes I should notify now, right? So that's the main idea why we have this interface. That sounds maybe a little bit terrifying in the beginning, that we tell you, you have to change the code to use it. But if we talk about microservices, and usually you have not so many resources open in microservices, so it shouldn't be that much code you have to change. Okay, and I told you already, somehow you implement the interface into this class, and now we need to register it somehow in the JVM. And for that, we need a so-called context. And this context you can get by calling core.getGlobalContext, which is a method in a class that we added to the JVM. And then it's a static one, and there's only one context in the JVM, because this context needs to know all the resources that are running in the JVM. So that means you have your class, you implement the interface first, then you get the core getGlobalContext, and then into this context, you register this resource. This is what you do, and usually you do that in the constructor or something of the class, but this is the place where it belongs to most of the times. So then this context maintains a list of all the resources that you registered in it, and it also keeps the order you registered these resources. And this is important if you, for example, have, let's say you have more than one class that use resources and they rely on each other. So usually most of the time, first of all, you establish a database connection. And then you have maybe another resource that makes use of this database connection. So that means the database has to be there first, and then the other resource. So if you now do a checkpoint, we first close the last resource you registered and go down until to the first one. So in the reverse order, you registered them. And if you do the restore, then we register them in the exactly same order you registered them in the first time. Right? So in this order, we call the after restore method. And in the demo, you will see how this works and why it makes sense. So creating a checkpoint, I already told you, we can do it from code, or you can do it from the command line. From the command line, we use jcommand. And you can either use it with the jar file itself, or you use the PID of the running program. And the command is jdk in capitals .checkpoint. And this will then call the JVM and say, now we create a checkpoint, right? The other thing is you can call core.checkpointRestore. The method name is a little bit misleading, because it really at the moment just creates the checkpoint and will shut down the JVM. So creating a checkpoint will shut down the JVM. And that's not a problem, because usually you do that just once, and then you deploy the stuff with the checkpoint. But since Tuesday last week or the week before, we already have the solution to create checkpoints in the background. So it means if you have the running application, we can let the JVM know that in case there's a checkpoint, it will create this checkpoint, but it will keep running. It could be reasonable to have this feature. So it will come with the next build that we will provide, just to let you know that there's also this solution. The next question is when to checkpoint. I mean, I showed you these graphs in the beginning, and I told you about JVM startup, time to first response, and JVM warmup. That also includes the application warmup. And in principle, it's your decision. Wherever you would like to create the checkpoint, whenever in time, you just do it whenever you like. But of course, it would make sense to do it at a specific point. And in principle, the best point would be if all the code is optimized and compiled, then create the checkpoint, because then there's no need to do more compilations or more optimizations, right? But how to find that point? So what we suggest is you run your application with a typical workload, and you start it with this parameter, -XX column plus print compilation. And what it does, it prints out all the compilation steps on the console. It sounds terrible, and it looks terrible, because it's like, it's scrolling like hell in the beginning. But if you take a look and observe the moment the compilations ramp down, so because at one point, most of the compilations are done, and that means if the compilations are done, the optimizations are also done, and then the code starts to settle at high performance. And this is a good point in time to create a checkpoint, right? This is just our suggestion. I mean, some companies also use code to warm up their application. For example, trading companies, they have specific code to warm up the software so that it's ready for high-speed trading, for example. And if you have this code, you can also use this code and then create the checkpoint at the end. It's also possible. You can also use tests, which do in principle the same. They apply some workload to all the methods, and then once that's done, it's also warmed up, right, and compiled. So, but this is just how we do it for tests. The typical usage of the CRaC stuff is you run your application in a Docker container. You create the checkpoint in that Docker container and store it in there. And then you commit the state of this checkpointed container. And the next time you start it, you start from this checkpointed container and then call the command with the -XX column CRaC restore from and point it to the folder where you stored the checkpoint. And this is the usual use case for that. Some words about compatibility. It's first of all only available on Linux x64 at the moment. This is because of Creo is only available for Linux. There might be an ARM port in the future. At the moment, we just don't do it because, yeah, building the JDK takes some time, and we just build it from time to time. Every couple of weeks, we build a new version, and we just build it for x64. And it's at the moment, it's only 17.02. That's the only one we have at the moment. But it's available for you to play around with. Of course, if it would be a part of the OpenJDK project officially, so the released one, and then it would be whatever version will come in the future, right? And we will probably also create ports for 19 and 20 and whatever. So then there's something that we call upgrade, and that means the JVM is smart. It compiles the code not only for the architecture, but even specifically for a CPU type and family of CPU. So that means if you have a Core i7 from Intel, then this Core i7 CPU has some specific features, and the JVM knows what to do with these features. And now you have a Core i9, which is even more capable, then the JVM can optimize the code for the Core i9. So you can imagine that if you have a checkpoint that contains optimized code for Core i7, you can run it on Core i9 because the Core i9 knows the stuff from the Core i7 because it's newer. If we take a look at downgrade, so that doesn't work at the moment. We are working on a solution, but we don't have it yet. So that means if you have, for example, a Core i9 and you create the checkpoint, you can't run it on a Core i7 because the code that is in the checkpoint was optimized for Core i9. So it has optimizations that the Core i7 CPU just simply doesn't know. So this is the so-called downgrade, which is not possible at the moment, but we are working on the solution here. And usually this is important because if you deploy something on node groups or in a Kubernetes cluster, then usually you have some, like I said, node groups, If you have Azure, for example, you have these node groups, and then it's guaranteed that in this node group, all the CPUs have the exact same architecture. That's fine, but you can run in a Kubernetes cluster, you can run multiple node groups. So that means you can have one node group running Core i9, and the other one can run Core i7. This would lead to problems depending on the checkpoint and where you created it. So you have to make sure that all these node groups have the same CPU architecture. In AWS, it should be the same. I got the information from some AWS guys, and they said, yeah, it should not be different, but I don't have really the exact answer there. For Azure, I know it's guaranteed that within a node group, it's the same architecture. And of course, once you have it in Docker, you can create the image, for example, on Linux, and you can run it on Windows and Mac once it has the same CPU architecture. So that means I can't really run a Linux image on that I created on an x64 Linux box on an M1 Mac. That won't work. But I can run it on an x64 Mac, which I do later on in the demo. So that leads me to a simple example. And it's really just to give you an idea. And what I try to do is I try to create an application that behaves in the same way as the JVM. So that means in the beginning, the performance is slow, and then it gets faster and faster. This is the behavior of the application. And what it does is it uses a scheduled thread, and every 5 seconds, it's calling into a loop from 1 to 100,000. And it creates random numbers in this loop from 1 to 100,000. And each number will be checked in a method if it's a prime number. So, and to make it more realistic and to get this behavior that I would like to see, I also have a cache. And the cache will just store the result. So is this number prime or not? And if the result is in the cache, then the prime number will return directly the result, which is fast because it comes just from memory, no computation needed. But if it's not in the cache, it has to calculate the number. And if it's a large number, it takes longer. And then it gets the result, it stores it in the cache, and then returns it. So this is probably slower, right? And to make it even more realistic, the cache forgets values. So it's usually if you have a cache, you don't want to keep the values forever, right? So you store them in the cache, and then they time out after some time that are not used just to keep the cache small. So, and this will start after 50 seconds, and then it will run every 10 seconds. It means after 50 seconds, once there are values that are older than 10 seconds, it will just remove them from the cache. Okay, so this is the behavior of the application. And that means the first run will be probably very slow because the cache is empty. Every value has to be calculated. And then from time to time, from each iteration to the next, it will get faster and faster because the cache will contain more values. So and I made some tests, and you see this is probably very similar to the curve that we saw with the JVM. So in the beginning, it's very slow, and then with each iteration, it gets faster and faster. Once it reaches the maximum performance, here is 1, and then it starts to level out. And this behavior that you see, this waves, is just because values have been removed from the cache, added to the cache, removed, and so on. So this is usually what you see when you run an application. It will never be flat at one level. It will always like going up and down a little bit. Okay, so the demo, the first demo is this application, and I have 2 shell windows here. And I do it in slides to give you a little bit of an explanation what I do. So I start my jar file, which is called CRaC for Java. I call it with the -jar command, and I add this -XX current CRaC checkpoint 2, and I say store the checkpoint in the folder CRaC -files. So in this folder, it should store the checkpoint, and then I start it. And the first thing that it does, it gives me the PID, and then the first thing it does, it registers these resources. In the first class is the generic cache, and then I register the main. In this demo code, it's not needed at all to register resources. I just do it to give you the idea, because I will also provide you the code for that demo. Just don't wonder that I do that, because for this code, it's not even needed to register resources, but it makes it more visual here. So the first run took 27 seconds, and the cache after that was filled by 63%. And then it was slow, right? Because the cache was empty. And then with every run, you see it gets faster and faster and faster because the cache get more filled and filled. So at one point we reach, for example, here 17 milliseconds, and then now we decide, oh, this is a good time to create a checkpoint. So I go to the second shell window and call it here with the J command, and I call the jar file, and with the command jdk.checkpoint. Right. So what happens then is that in the other window where we have the running application, it will call the before checkpoint methods, and it will call them in the reverse order. You see, I first registered generic cache and then main. It will now call main first and then generic cache, which makes sense. And then it will create the checkpoint, and then the JVM will be killed. So, and this is, in this example, this is the JVM warm up, right? Because I warmed up the cache. This is my application that I warmed up. This application is so small that the whole startup time is so fast, it doesn't really make sense to measure it at all. So now I killed it and I'm waiting. And if I wait for a minute, or I wait for a day. So what will happen? So the first time I start the application, and I told you the cache will forget values that are older than 10 seconds. So that means I store a timestamp with each value to figure out when it's outdated. So the first time I start it and it will hit the cache will figure out, oh, wait a minute, all the values are timed out, and it will wipe out the complete cache. And this will happen. And I tell you that you are aware of, if you have time-dependent data, like session timeouts, for example, if you have something like that in somewhere in your checkpoint, be aware that once you start it, the time it's right. So it went on, and so that means these things are not valid anymore. So usually either you don't store time-dependent data in the checkpoint, or what I did here is in the before checkpoint method. So at the moment I create the checkpoint, I store the current epoch seconds in a variable, and that means this variable will be part of the checkpoint. When I restore, I just read this value that I stored, and I know exactly when the checkpoint happened in epoch seconds, and I just get me the current epoch seconds, calculate the delta, and then apply this delta to all values in the cache. And with this, all values are valid again in the cache, right? So, and not invalid. And that leads then to the fact that if I restore it like this, like Java -XX CRaC restore from, I pointed to the same folder where I stored the checkpoint, then you see it will start up pretty quick, and it will call the after restore methods in the same order I registered them in the beginning. So that means it's now in the same state as after startup, which makes sense. And then it will continue from iteration 12, because I stopped it at 11. And then you see at 12, it will just restore. The cache is completely filled as it was before, and the time is fast, and it will stay fast. And that's pretty impressive. So that means I really took the state at that point in time, and then at another point in time, I just can restore from there. And all this warm up of the cache, I don't have to do anymore. And this is the time that we save, right? And if we transfer that to JVM startup, that means all the compilation and optimization steps. This is already done. It's part of the checkpoint. So it means from that moment on, I don't have to do that anymore. Okay, so if you would like to play around with it, you can just get this demo program at my private account, like github.com/hansolo/CRaC4. And I just provide that you can download the JDK, you can download the code and then directly start, and this will work. So you don't have to play around with it and figure out how it works, and you can start from there. That's all cool. I mean, I showed you a demo in slides and told you, hey, it's so fast, right? So cool. But of course, we did also test with real frameworks. So the question is, how good is it really? And for this, we took Spring Boot, Micronaut, Quarkus, and some XML transform, and we measured the time to first operation, right? This is what we define as the JVM startup. And for Spring Boot, it took 3.9 seconds. Micronaut was around 1 second, and Quarkus 980 milliseconds, and the XML transform 4.3 seconds. This was running on a plain OpenJDK. And once we restored from the checkpoint from CRaC, it was this. And you can see that's pretty impressive. This is in the range of native image startups. So even if the startup time of Spring Boot was 3.9 seconds, now it's 38 milliseconds. And Quarkus was 980, but it's also only 33. And the XML transform went down from 4.3 to 53 milliseconds. So the reason for that is that the red bars contain the whole compilation and optimization phase. And after that, we created the checkpoint. The blue bars, it's really just loading from I/O. We just loaded from the disk into memory. And that's the reason why it's more or less the same speed. It only depends on the size of the checkpoint and how many resources you have to restore. But that's it. And that's the reason why the startup times are more or less the same for all of that. And once I said that already, so when we create the checkpoint, we compact the heap. And that means we create a set of files, which is for this demo that I showed you, it's around 30 megabytes. It's more or less the heap that we save, right? Like a heap dump, you can think about that. And it's a couple of files, maybe around 20, 30 files that we save. And you are right, the larger the heap, the larger the checkpoint files. But still, loading something from a modern SSD drive back into memory is really fast. So this is always faster than starting up the JVM, right? Okay. So this is that, and just to let you know what we did. First of all, these demos are available. So if you don't believe me, you can just try it out yourself and see the results. For Spring Boot, we patched Tomcat with CRaC and then told Spring Boot to use this one as the embedded web server. Micronaut, we did something similar in Quarkus too. So for Micronaut, there is already an implementation of CRaC. So they support it. And they support it in a really great way. So you don't have to even implement the interface anymore. You just add an annotation. I don't know exactly, but something like CRaC. And then Micronaut, the framework, will take care about all closing the resources and reopen them, which is great. Quarkus is also, they have a prototype working which supports CRaC. And since last week, Tuesday, I think, we are also in touch with the Spring guys. And they are also interested in adding support for CRaC to Spring, which is great. So as a summary, CRaC is a way to pause and restore JVM-based application, and it doesn't require a closed world as with a native image. So that means the native image needs to know all the classes that will be loaded before it will compile them, where CRaC is just a JVM. So even after the checkpoint, you can load classes dynamically, and they will run and will be optimized by the JVM. And the benefit is potentially extremely fast time to full performance. And we somehow eliminate the need for detecting hotspots, and we don't have to compile methods, recompile, de-optimizations, because this is all done before we create the checkpoint, right? So once we went through this phase, we create the checkpoint, and then we don't need to do that anymore. And with this, it improves throughput from the start. And it's an OpenJDK project, and it can also save you some money. So to explain that a little bit, you might probably see or know these kind of graphs if you're working with cloud infrastructure. So in Java, then usually you see this on the y-axis, we have the CPU utilization, and on the x-axis, we have the time. And then you always see this peak in the beginning, and then it falls down and levels out at some specific value, the CPU utilization. And the reason for that is that this is the JVM startup time. And this is mainly interpretation and compilation, optimization, and all this overhead at the beginning. So, and there are companies, they buy nodes that have lots of CPU cores just to get rid of this startup time to make it as fast as possible. But once it is done, they don't need this many CPUs anymore, because you see the CPU utilization drops after the first initial peak, right? So if we create a checkpoint here and start from there, then you don't need that many CPU nodes to run the same application, right? And that will save money, because memory usually is not the cost driving factor, but it's the number of CPU cores, which is really expensive in the cloud. And with this, we eliminate startup time and CPU utilization. Still, the memory footprint is larger than with the native image, that's for sure. The whole thing, that means the OpenJDK build and also all the demos you can find at github.com/CRaC. And we also have a demo for Amazon Lambdas, because they also suffer from startup time. So you can find all the stuff there, and also all the information is there. And now let me give you the real demo. Therefore, I go to my shell windows here. So what I do is I have this little application that I showed you. I created a Docker image, and in that Docker image, I run this application now without any optimization. So see, it's the first start, and it will probably take around 28 seconds for the first run to complete, because the cache is empty. It needs to fill it, going to the 100,000 random numbers and check them for prime. And this, if you imagine this would be the time to first response, then yeah, it would be not so good, right? So, and I was surprised at Java 1. I heard about some people that had a problem with the application and the startup time. The startup time to first response was 40 minutes. 40 minutes. I never heard about that, but okay. But even this with 28 seconds, and now you see it's getting faster and faster, but it's still, the time to first response to the first output was, let's say, 28 seconds. It's not that great, right? So, okay, I created a checkpoint in that container. And now I restore the same thing just from the checkpoint. And I did the checkpoint at iteration 17. So that means when I start it now, it should restore from and continue counting from 18. And the important part is, once I click the button, you will see it will directly go and continue and then give me the first response. And then it will wait for 5 seconds, right? Because it will call them the loop every 5 seconds. So I start it now. And there you go. And it's now every 5 seconds, and you see the cache is filled and it's fast. I don't have to wait. So that means the calculation time is always in the 20 to 30 milliseconds. And because it's Docker, I can also start it a second time, right? On the same machine in a different container, and still it will start from the same point because it's the one checkpoint that I created. And if I stop it and restore it, then of course, same thing. It will start from 18 from that checkpoint. And this is more or less a demonstration about JVM warm-up, because what I really did was I warmed up this cache and then created the checkpoint, and now I start with the warmed up cache. I also have a demo for plain startup time. And let me see if I can find it, because I just created it today. Second. This is the one. So I started up the first time. This is really now startup time. And what I did is I have just one class, and in the main class, in the constructor, I just fill fill a map, right, like a cache with the 100 numbers from 1 to 100,000 with this prime result. So that's what I do. It takes around, or maybe 50,000, it takes around 8 seconds. So I started, and you see the plain JVM startup time is just 41 milliseconds, but my code now takes longer to optimize. So I think it's around 8 seconds. So we would see that. Here we go. So at 11 seconds, that's the time to first response. So now I created a checkpoint, and I did that after this was run. And now let me restore this one. Restore. And now you will see, oops, it's not, oh yeah, sorry, my fault, wait. I have to give it a name. So now, and there it is, 2 milliseconds, right? And this is because now the cache was there, so I don't have to do this stuff anymore. So I just do it with the startup time. You see, with this, you really can do time to first response. You can reduce it dramatically just by using CRaC. And it all depends on the point in time where you create the checkpoint, right? So this is the main factor here. If you would like to warm up your application, you can also do it in main, then you only save the plain startup time of the JVM. It depends on you. So this is, in principle, what I have to show. And with this, I just say thank you for listening. And now we can do questions if you like. Let me just stop my sharing, then I can see the chat. Okay. Oh, I don't know how we would like to do that. If there are questions.
I guess there was at least two questions. One is, where can we find the slides?
The slides are on SlideShare.
Okay.
If you look at SlideShare, wait, I can give you give me a second.
Yeah.
I will just look it up and give you the link. And like I said, this is a little bit older version, but not really that much older, because I really change them all the time. I changed them directly before we did the session here again. So here we go. Wait, I put it in the chat. And there we go. So there are the slides. Okay, this demo, it was Mac OS with Docker. Yes. What I did was I created the demo on a Linux machine, which is a Core i7, and created the Docker container there, and then I just put it on Docker Hub and pulled it on my Mac and run it in Mac. Because it's the same architecture, you can run Linux in a Docker container on Mac, and we also tried that on Windows, and that works too. So it really, you just have to make sure that it has the same architecture. So that means if you create it on Core i7, it should be equal or greater than the Core i7. So then you can run it on Mac, on Windows, whatever. But this is the only restriction that we have. Was there anything else? Is the pitch sharing an exception? I'm just reading through it. There is the pitch sharing an exception for JVM snapshot? Yes, the problem is typically in a container with the PIT, it's not a big deal because usually the Java application gets PIT number 1. And that's not the big problem. Like I said, we are working on something to get rid of this PIT restriction. So at the moment, the PIT is part of the checkpoint, but we are also thought about when we do a restore, just use another PIT to do it if it's taken. This is possible, but it's not implemented yet. So, but we are working on a solution for that so that there shouldn't be any problem if the PIT is already taken on the target machine, right? So it's at the moment, it could be that if there's another process that uses, for example, PIT1 and your checkpoint has the PIT1, then it won't work. But this is a limitation in CRaC, but we can get around that with the other solution. But this is just work in progress. It's not done yet. Let me check if there was something else.
I think Shyam had a question, but I think Shyam basically asked the question on the chat itself.
Yeah.
The end.
Where is it?
The end of the chat.
Good question. Okay. Where is that one? If you have it handy, you might want to tell me which it was.
It's
how frequently the versions will be upgraded? Okay. At the moment, it's really if we have time. And if you check the GitHub/CRaC repository, you will find there's something like OpenJDK releases, and you will only find 3 in there. And the last one is probably already a month old. Usually we just collect some issues and then we create a new OpenJDK release. So it's not really bound to any public OpenJDK release at the moment. It's really because you have to think about it like Project Jigsaw that we had in the JDK. It was for years in the OpenJDK project before it became part of OpenJDK. And this is the same. So all the other projects the same, like Loom. Loom was not built on each iteration of the JDK. There was one for 17 and for 19. So, and we do the same. So it's like a sub-project of OpenJDK, and we decide when to build a new OpenJDK with CRaC. But usually we try to make it at least once a month, if it makes sense. So if there's nothing really new, then it's not needed. But because now we added this functionality that we can keep the JVM running once the checkpoint is done, this will probably, within the next week, there will be a new version of it. Yeah, there's another one. That's a good one. CI/CD systems. I'm currently working on a demo to show how that works. And especially because I also tried GitHub runners, and in the GitHub runner, I'm not sure how you can define the CPU type, if it's possible at all. I know if you do it in a cloud environment like Azure or Amazon AWS, you can define it. GitHub Actions is a good question. I have no idea how that works. I just know they have x64 runners, but if they have the same level, the CPU level, I don't know. That's the reason why I'm trying to create a demo for that, because this is a good question. Usually, I told you, you create a Docker container, you run the application in there, and then you have to create the checkpoint in the Docker container, and then you have to store that state. And even this is not easy doing in a CI/CD system, because you create the Docker container, start it, then you have to log into the container, create the checkpoint, and then you have to store the state of this container, and this should be then be deployed. And this is a little bit tricky. And yeah, like I said, I'm working on that, and there will be something in the future. We need to show that how to do that. Then there is one other. What's that? Seems like you might need to have customers doing it. Yeah, so it's really, like I said, CI/CD is with this kind of stuff not easy. The same goes, by the way, if you do JVM native image, they have the same problems when you really use the enterprise edition and you need to create the profile and then apply that to the process. That means you have to run it first, take the profile, and then create from this the native image. So I was in touch, I'm in touch with the JVM people, and they have exactly the same problem with this CI/CD systems and how to set it up correctly. It's not so easy. But yeah, like I said, we are working on that, and hopefully soon we have something running that we can show you. And if this is there more? I don't think so, right?
Nope, that's about it.
Okay, if there's something else, you can reach me on Twitter, @hansolo_. This is the only social media platform where you can reach me. And I would love to see people trying it out. And if you stumble upon problems, just put an issue in the GitHub repository. And even if you just have questions, put an issue there with a question, and we will try to keep track of that. Or if you run into problems, just let us know, because we just create this feature, but we don't run applications on it, right? We just run our own demos, and of course they work, but we would like to see really applications running on that and get the feedback, what we could improve or what would be useful. For example, what we will also provide is probably a way to have the checkpoint time inside of the JVM. So once you create the checkpoint and you do a restore, then you can just ask the JVM, let me know what was the checkpoint time, so that you don't have to keep track of this kind of stuff. But this is also, we have a list of stuff that is to do. And like I said, if you have things or ideas or problems, just let us know and we try to fix it.
That was really interesting. Thanks a lot. Thank you for
really cool.
for staying up late as well for us. So thank you so much.
Of course.
Yeah, if there aren't any other questions, then we could wrap it up and give everyone their Friday evenings back.
Actually, can you hear me, Sirisha?
Hey, Don.
Hey,
Hi.
I just want to say hi, Gerrit. I just got home. I had an appointment, so I'm glad I could log in at the very last second to say hello.
Yay! Your t-shirts, I have them here.
You do?
Here, this is
well, not my t-shirts anymore. Hopefully they find it to the rightful owners.
Yeah, this one's right.
Yeah.
Yay!
Yay!
They are under my desk, ready to be delivered.
Awesome, thank you.
Okay.
Thank you so much. Thanks, Don.
Okay.
For cheering up. Everyone else, thank you so much. Have a great weekend.
Yeah, and we'll have the session uploaded on YouTube within probably a few days. But thank you so much, Gerrit, and thank you, everyone.
Okay.
Thank you.
Take care.
Bye, everyone.
Bye-bye.
Bye.
Bye.
Bye.